So, dear colleagues, it's 3 minutes past 11 on the clock. So I think it's high time to start our sixth MARCOGAZ Tech Forum. So my name is Frédéric Vulovic, and I work for Natron, which is one of the two French TSO. Our former name was more well-known, it was GRTGaz. I'm the head of the expertise and engineering department in charge of measurement within Natron. I'm also the vice chair of the MARCOGAZ Group 5 dealing with gas quality and metering. And today it's my pleasure of mine to moderate this tech forum dedicated to LNG quality. So this webinar has a duration of 1 hour and a half, and we'll go through some insightful presentations of José Lana and Jörg Leicher. So feel free to send your questions on the chat during the interventions, but something important, we'll actually only address the questions during the Q&A session at the end of the webinar. The recording and the slides will be actually available on the MARCOGAZ website in the next days. So I don't want to waste too much time. So now I will leave the floor to Alexander Schwanzer, the president of MARCOGAZ, to deliver the opening speech. Alexander is a member of MARCOGAZ board since 2008 and president of MARCOGAZ since June 2024. And after 2 years as vice president. So in Austria, he's the head of the certification body at the Austrian Association for Gas and Water, OVGW, for products, people and companies in gas, water, and electricity sector, as well as a representative for European gas affairs. He's active in the industry for more than 25 years, and he's an experienced strategist with an extensive network and wide-ranging expertise in gas and water sector. He serves on several standing committees and working groups at the OVGW, Austrian Standards, CEN, MARCOGAZ. Alexander is also organized the MARCOGAZ Gas Tech 2018 in Vienna. His education includes a master's degree in industrial engineering, building technology, and supply business. So, Alexander, the floor is yours.
Merci, monsieur. Thank you, Frederic, for your very kind introduction indeed. And very good hello and very good day, ladies and gentlemen, to our MARCOGAZ webinar tech forum on LNG quality. First, we would like to briefly outline the place of LNG in the EU energy policy and address the topic in general, already highlighting the points for LNG at the first stage. So next slide, please. So the EU energy policy, as you know, is based on the principles of decarbonization and competitiveness, decarbonization and security of supply and sustainability. And you know, its objectives include ensuring the functioning of the energy market and secure energy supply within the EU, as well as promoting energy efficiency and savings, the development of renewable energies, and emphasizing interconnecting of energy networks. And a variety of measures aiming to achieve a complete energy union is the core of the EU's energy policy. According to the Energy Union on the slide, the 5 main aims of the EU's energy policy are to, and here at this point, we would like to emphasize the fundamentals relating to LNG from the main objectives. It is, of course, to diversify the Europe's source of energy, ensuring energy security through solidarity and cooperation between EU countries, to ensure the functioning of a fully integrated internal energy market, enabling the free flow of energy through the EU through adequate infrastructure and without technical or regulatory barriers, and of course to reduce the dependence on energy imports. So I leave the other items because we're just focusing on the relevant items for LNG. Next slide, please. So regarding our achievements within the European community, our general political framework is considered as a special achievement of EU energy policy. And behind every energy policy, ladies and gentlemen, is also a strategy for this energy union, which aims to give EU households and businesses, of course, a secure, sustainable, competitive and affordable energy supply. And the current energy regulatory framework has been adapted with the EU Repower Plan. And this plan envisages a rapid and complete eliminations of dependence on fossil fuels from Russia, as you know. And this plan includes, among other things, of course, firstly, the diversification of energy imports. The EU has been working intensively with international partners for several months to diversify energy supplies and curb rising energy prices. And to this end, the member states have established a new energy platform for the voluntary joint procurement of gas, LNG and hydrogen. And this energy platform will perform three key functions in joint gas procurement. Firstly, as you know, is pooling and structuring the increased demand we have in Europe to optimize and transport the use of gas import, storage, and transport infrastructure, with the aim, of course, of maximizing security of supply and replenishing storage capacities. And in addition, actions at the international level. The increased joint activities at the international level will focus on establishing long-term cooperation framework with trusted partners through agreements that include, among other items, the procurement of gas, LNG and hydrogen, fully, of course, leveraging the collective strength of the Union. In addition to these diversifications, of course, a part of this energy platform is to doing smart investments. The Commission analysis shows that additional investments of more than 200 billion are needed under the Repower Plan by 2027, in addition to the funding of already provided. And as you know, ladies and gentlemen, storage is crucial for improving security for supply. Therefore, projects to expand storage and offtake capacities should be adequately supported, of course, financially as well, to ensure better preparedness and response to risks related to gas security of supply. Smart investments includes also importing sufficient quantities of LNG and pipeline gas from other suppliers, and this will require an estimated 10 billion in investments by 2030 to ensure adequate gas infrastructure, including LNG import terminals, pipelines connecting unused LNG import terminals to the EU grid, and better return flow capacities. Those items being here listed can also find, for instance, in those two legal provisions here on the shade. So, and the next and last, third step in our last slide, please. We know to the current situation that the EU gas demand is around more than 300 billion cubic meter per year. Natural gas currently represents around a quarter of the EU's energy consumption. About more than 26 of the gas is used in the power generation sector and around 23 in industry. Most of the rest is used in residential and service sectors, mainly for heating buildings. And to the current situation, following the Russian invasion of Ukraine in February 22 and its weaponization of Europe's energy supply, the share of Russian pipelines gas in total EU energy imports has fallen dramatically from more than 40% in 2021 to about 18% in 2024. And this has been replaced mainly by LNG from the US, which has supplied more than 45% of the EU LNG imports in 2024, and reliable pipeline gas imports from Norway, North Africa, and Azerbaijan. And regarding the global LNG supply, ladies and gentlemen, the current situation is expected to continue to rise slightly in 2025, driven by increase in production and liquefaction capacities in LNG exporters. And this will ease the pressure on global gas markets and lead, together with historically high level of gas stocks and subdued demand, to lower prices on the European markets. The largest LNG global exporters in 2024 were, by the way, the US, Australia, and Qatar. So now going on our surroundings in several EU countries, they're increasing their LNG import capacity by accelerating investments in LNG terminals. The EU's LNG import capacity grew by 70 billion cubic meter between 2023 and 2024, and an additional 60 billion cubic meter are expected to become operational between 2025 and 2030. And you see the huge amount which is required. And at this point, MARCOGAZ takes over his work and responsibility, because there's currently no public database which current information on the quality composition of LNG by origin. Due to these numerous liquefaction terminals and the commissioning of new countries over the past decade, the available information is no longer complete. So for this reason, the MARCOGAZ Working Group 5 has taken its responsibility and has decided to conduct a survey among its members in 2023 to collect current data on LNG quality. And this is intended to facilitate decision-making for natural gas market players in the current natural gas supply in Europe, and to ensure compliance with the relevant EU standard, as you know, EN 16726 and EN 437 for transit. And at this point, ladies and gentlemen, I will hand over the floor back to Frederick, our kind expert from MARCOGAZ Working Group 5, and to José, and as well Mr. Jörg Leicher. Thank you.
Thank you very much, Alexander, for your introduction and for this first data on LNG in European energy policy. Our next speaker is José Lana. So José holds a degree on chemistry science at the University of Zaragoza in Spain. He has more than 35 years of experience on innovation, R&D activities within Enagás. From 1998, he participates in many research and innovation projects in the field of LNG, gas transmission and distribution, and utilization of natural gas and now renewable gases, with a special focus on safety and quality issues. He's currently working at the Innovation and Technical Development Department as R&D project coordinator and gas quality expert, working on projects for studying different aspects of natural gas quality, hydrogen impact in transmission pipelines and underground storages. He's a member for years now of several European groups dealing with natural gas and new gases quality, such as NSOG, Easy Gas, and of course MARCOGAZ, and other groups like the Technical Study Group of GNL. He's also participated in the same working groups dealing with gas quality. Finally, Jose is currently the chair of the Group 5 on the gas quality and metering of MARCOGAZ. So Jose provides us into current state of LNG quality database. Please, Jose, your time is now.
Thank you very much for the presentation, Frederick. I'm sorry, I have some cough. Okay, next slide, please. Well, first of all, why MARCOGAZ did collect liquefied natural gas quality information? I think that Alexander has said something about this previously, but the reason is described here in this slide. On the one hand, the most cited source in different publications is the GIENL, but the table from the GIENL is coming from a 2012 report, so has been quite old. This table is available in later reports or recent reports, but it's always the same. So I know that GIENL has made some trial to update information, but has been not possible due to several reasons. On the other hand, during recent years, many liquefaction terminals or expansion of oil ones and new countries have started operation. That means that the database collected more than 10 years ago is no longer complete. We have new sources or from some countries, new liquefaction terminals. Additionally, as already mentioned by Alexander, natural gas supply scenario changed dramatically in 2022 due to the war in Ukraine, where the Russian gas deliveries to Europe decreased dramatically. This means that new sources of natural gas appear in Europe, and most of this was LNG. So, after discussing these points and the impact in gas quality that the new LNG sources can have in Europe, in the former working group gas quality of MARCOGAZ, that is his activities now carried out by G5, we agreed in 2023 to launch a survey amongst MARCOGAZ members in order to collect quality data of LNG. The aim of this was to help decision to the natural gas market actors in Europe in the current supply scenario in Europe. Next slide, please. So, what is the scope of work that we agree? After a couple of rounds of discussion, we finally agree with this scope of work to collect LNG composition data from MARCOGAZ members managing LNG terminals. We want the data from each individual cargo download in an LNG terminal. So we don't want average data. We want the real data of the quality download in any terminal and for each cargo. Also, we ask for all information from cargo coming from liquefaction terminals, no reloading operation between LNG regasification terminals. This is a very interesting market if you are a shipper that consists in download LNG, I don't know, from Qatar, for instance, in Spain, and then to reload the LNG and send to Italy. But in this case, we cannot guarantee that that LNG has the same quality than in Qatar, perhaps because he has been blended in the tanks in the LNG terminal with another quality. So we want only data from the country of origins. The idea is to use this information to calculate the main gas quality parameter from different origins. On the one hand, we will give an average gas composition, including the standard deviation, but also the maximum and minimum of each LNG component in order to know what could be the maximum percentage of this component in the LNG. And additionally, we decide to calculate the main gas quality properties for gas utilization, as can be seen: gross calorific value, Bove index, relative density, and methane number. What we presented is the average of all the cargos, so the values corresponding to the average gas composition. But also we give the range of maximum and minimum values. Next slide, please. Well, some consideration regarding the scope of work. It is known that the composition of LNG slightly changes during ship's transportation, because the LNG is transported at atmospheric pressure in refrigerated, in isolated tanks in the ships. To maintain the LNG in liquid state, some LNG is evaporated, taking heat from the LNG and maintaining cold. That means that the lighter components like nitrogen and perhaps methane are evaporating. This means that the LNG arriving to the downloading terminal is not exactly the same that in the country of origin. But anyway, we consider that this change is not very relevant. In any case, the information collected from MARCOGAZ member LNG terminal will show approximately the maximum range of composition and property that can be expected of a specific LNG origins at the arrival in Europe. That means that, for instance, again from Qatar, it's not the same to take the LNG to Greece than to the Netherlands. There will be a small difference, but we think that with the exercise performed, we are able to collect the maximum runs that you can expect. The information collected and presented is of the LNG arriving to the LNG terminal, not the natural gas injected into the national transmission network. Normally, except in the new FRSU terminals, all the LNG terminals has several LNG tanks in which the LNG arriving is blended with the LNG that is already in the terminal. So the composition that we are going to inject in the national transmission network will be different to the composition of the LNG downloaded in the terminal. Anyway, any natural gas injected in a network at the exit of the LNG regasification terminal shall be inside the runs defined by the applicable national natural gas quality regulation of specification. I mean, if the LNG is outside the national specification, the LNG terminal needs to do something to adjust the quality to the national gas specification. This is done, for instance, in some terminals in UK or in Italy, but it's not a normal practice in most of the LNG terminals in Europe. Finally, important to say that no information about the LNG downloaded by cargo, volume or energy has been collected. This is considered as sensitive information. For this, we have given the report some reference to GINL reports that are very interesting in order to know what is the LNG market. But we are not going to give this information. We think that one of the problems in the updating of the GINL database was the commercial issues associated to the different origins of LNG. We will try to avoid to present any type of information that could be considered sensitive or attached to commercial issues. Next slide, please. Well, then we prepare a questionnaire and we send to our members. Due to several reasons, we only receive information from 7 members of MARCOGAZ to the database. Some members are with confidentiality clause in the LNG terminals that avoid him to send information about the LNG quality. That is a normal procedure between LNG terminal operator and LNG shippers. So we understand and it's a pity not have that information, but we do our best with information that has. The information collected covers the year 2022 and 2023 for most of the terminals. In total, we have collected 760 individual cargos from 5 European countries. That means perhaps about 10, 12 LNG terminals. And this is the information that we have used in our analysis. I have to say that another member sent additional information, but after looking to this information, we see that the format of the data or the structure of the data didn't allow to process in the same way that the pure composition of the LNG. But anyway, we are very grateful to this member for the effort done. The information we receive include LNG from 17 exporting countries. And I have to say that although this is not the optimal situation, we would like to receive more information. We think that the amount of information received is considered sound for representing the current LNG quality received in Europe. Next slide, please. Well, the analysis of the data that we have performed, on the one hand, as I mentioned, is the mean average composition of the LNG from exporting country. This information includes the maximum and minimum of each component and also the standard deviation. Also, we have calculated the main properties, as I mentioned, Bove index, gross calorific value, density, relative density, and method number. And also, we present the average and the maximum and minimum value per origin. And although from some origins only few data are available, for many, we think that the number of cargos collected give the information a quite sound statistic value. So perhaps we have a couple of countries with only one cargo. Okay, perhaps there is chance, but for another countries we have more than 200 cargos. So that seems that is statistically quite sound, the information collected. Next slide, please. Well, going to the different results in composition, we produced tables in which we shown the country of origin and number of cargos, the average value of each component in mole, the maximum value of each component, the minimum value of each component, and the standard deviation. Some remarks. Carbon dioxide is not considered because it's not a normal component present in a measurable amount in LNG. Most of the CO2 is eliminated from natural gas during the treatment of the natural gas before liquefaction. These are the main difference between an LNG and natural gas coming directly from the gas field, the absence of CO2. Sorry. Also, neopenthane is not considered because its presence is almost negligible in LNG, and besides, most of the gas chromatograph used by the LNG terminal operator didn't detect it. Anyway, as I said, the amount is almost negligible, so there has not an impact in the quality of the quality of the LNG. And finally, also oxygen is not collected because it's not a normal component of LNG. I have to say here that in recent years, the presence of oxygen has been reported in some cargo manifestos arriving to Europe. But this amount is normally very small, with no impact on gas properties. And additionally, most of the LNG terminals are not analyzing oxygen when they analyze LNG. Next slide, please. Well, and this is an example. In the report that we have published, you can find for the 16 sources the full tables. As you can see, in this case from Qatar, Russia, Trinidad and Tobago and USA, we have the number of cargos, quite representative, I think, and then we have the average composition. The average composition, except if there is an error, should sum 1. Not the same with the maximum and minimum. Next slide, please. Then, with this information, we have calculated the gas properties. The gas properties has been provided in the report in tables and graph. For the calculation of the properties, we have presented them in ISO 15115 conditions and following the ISO 69726 standard, that is I think is the most used or the only used in the gas sector for calculating gas properties. And for the method number value, we use the Annex A of the EN 16726 standard. Next slide, please. And this is the result as we have presented. You can see, in this case, for some of the information received, again, the number of cargoes for each of them. As is the case of Emirates, we have only one value, so we have only the average. That is the measured data. We have calculated the GCV, the BOVE index, and relative density. But for the other origins, we have seen here the average data, but also the minimum and maximum value calculated for the different properties. If we see this data in a graph form, next slide, please. What we have presented here is the average and the maximum and minimum. The average is the dot, and the range, maximum and minimum, is the vertical bar. As you can see, for several countries, there are very few, the range of the delivery is very small. That could be possibly due to the lack of a lot of data. But for another, the range is very, very wide. We are not analyzed the reason for this in the report. It was outside the scope, and we think that for doing that, we need a lot of more knowledge about the LNG market that we can have at this moment. For instance, in the graph for Egypt, you see that the gross calorific value or the BOVE index range is quite wide. This was quite surprising to me because in Egypt there are only 2 liquefaction terminals, so the width shouldn't be so wide. But okay, perhaps it's an outlier. I don't know. We have not done that analysis. It's not surprising, for instance, the value for Qatar or from USA, because in both countries there are many liquefaction terminals, each one of a different time and with a different technology. That means that the LNG will be slightly different from terminal to terminal. Also, in the case of Qatar or USA, we have an impact of the traveling time that, as I mentioned, have a slight impact in the gas quality, which means that the properties will be slightly different if we are analyzing data taken in Greece or taken in Spain or taken in the Netherlands. So in this graph, you see the BOVE index and gross calorific value. Anyway, as you see, it's not very width, no more than 3 megajoules per cubic meter, the width of the BOVE index received in Europe. So it's not a very bad information either. Next slide, please. Here we have the relative density. We see in the spread of the properties from different countries are correlative with the gross calorific value and BOVE index. The countries in which the range of these properties was higher appears the same in the case of the density. Next slide, please. And finally, we have calculated the method number. As you can see here, method number is going from 70 to almost 95, depending the origin, but most of the LNG received is about 75. So next slide, please. So for concluding, what I can to say is the MARCOGAZ Group 5 has carried out the exercise of collecting LNG composition information. We analyzed more 70 760 cargos, arriving to 5 European countries and from 16 exporting countries. The main properties of the LNG has been calculated and presented in the report, but as we have presented and give the information about the composition, anybody can calculate other properties or calculate the same properties using another calculation method or standard. And finally, only to say that the process has been described and published in a report that is available on MARCOGAZ website. And I think that's all. Thank you very much for your attention.
Thank you. Thank you a lot. Many thanks, José, for this nice overview of the LNG data survey. I see that some people are reacting. I just would like to remind you that you can ask questions on the chat, and feel free to do so. And we'll come back at the end of the presentations, after the presentation, during the Q&A session, we'll answer your questions. So our next speaker now is Jörg Leicher. So Jörg is actually studied mechanical engineering at the Ruhr University in Bochum in Germany, where he received a PhD in 2006 for his work on numerical modeling and combustion processes. From 2007 to 2008, he worked as a postdoc at the Institut Français du Pétrole, IFP, in Lyon, in France, before joining ANSYS in Germany, in Munich, as a CFD support engineer. Since 2009, he's been working in the Department of Industrial Combustion Technology of Gas in Wärme Institute Essen-EV, a research center which is focused on applied research into energy-related topics. Here, he's currently in charge of the numerical simulations group. His professional interests include the use of alternative fluids like hydrogen, ammonia, biogas, or syngases in large-scale technical combustion processes, such as industrial furnaces and power plants, the decarbonization of process heat in general, as well as the impact of fuel quality on gas-fired equipment and appliances. He serves as a member of several national and international committees on issues dealing with gas utilization, renewable gases, and natural gas quality. And within MARCOGAZ, he's active on the gas quality and metering group 5. So Jörg will be giving us a presentation of the role of GNL quality when designing industrial gas. So now the floor is yours.
Well, thank you, Frederick, for the kind introduction, and good morning, everybody. It's a pleasure to be here, even if it's only virtual. And José talked a lot about gas quality, LNG quality. I want to tackle the same issue, but from the other end of the gas value chain, because I want to talk about what fuel quality, what gas quality, what LNG quality actually means for end users. And I'm going to focus on industrial gas users, because in many ways their requirements are often a little bit different compared to, for example, the residential sector. Next slide, please. I think we've seen a similar slide before in the first talk. This is what you see here. This is the distribution of natural gas across Europe. And as you can see, about 20% or so of the gas consumption is accounted for by the industrial sector. There is a significant spread here. For example, if you look at Germany, industrial gas consumption accounts for almost 40%, because we have a lot of energy-intensive industries. So keep that in mind. This 20% is a European average. And what's interesting here is that if you look at industrial gas utilization, there's actually two main pathways how gas is being used. The first one is the chemical route, where gas is basically used as a chemical feedstock for all kinds of base chemicals, for example, in fertilizer production, in hydrogen production today. That makes up about 10% of the industrial gas consumption. And the more prominent, and we're going to leave that be for the moment because that's extremely specific. We're going to focus on the second pathway, the more prominent pathway, which is using gas as a fuel, and in particular, using gas as a fuel for process heating. So process heating means we need heat for some kind of manufacturing process, and you can see quite a number of different industries being mentioned here with their specific consumption rates of natural gas for process heating. As you can imagine, it makes a lot of difference if you, for example, produce steam in a brewery, in the food industry, or if you want to melt glass. The processes, the products, the requirements, and also, of course, the technologies involved are going to be very, very different. And this is one of the key features of industrial gas utilization. It's extremely specialized, it's extremely heterogeneous, highly optimized, and it's always an indirect use of gas. It's always about a product, so we have this aspect of product quality to consider, which is something that, for example, you do not find in the residential sector, also not in power generation. It's also worth pointing out here that we have to think not only about energy flows, but also about temperatures, because we need process heat at very different temperature levels. If I wanted to think about steam generation, I'm working in the low temperature range, or if I think about drying processes in the food industry, for example. On the other hand, if I look at energy intensive basic materials like metals, like glass, like ceramics or so, then I'm talking about much higher process temperatures, and process temperatures can go up to 1,600, 1,800 degrees or so. So that's also something that we need to keep in mind. It's not only about the energy flows, it's also about the temperature levels that we need. Next slide, please. However, if we think about gas as a fuel, then we can simplify things a little bit. And please keep in mind, this is a simplification here. But basically, every technical combustion process can be characterized by two process parameters. And the first one, this is the firing rate, which basically tells me how much energy is being introduced into the combustion process with the fuel. And the second important parameter is the so-called air access ratio lambda, which tells us how much air or oxidizer in general is being introduced into the combustion process compared to the theoretical minimum amount of air that I need. You know, if you want to burn something, you do not only need a fuel, you also need an oxidizer, which usually is air. And note that both these key parameters are directly dependent on the fuel composition. If you want to calculate the firing rate, you need a calorific value. Usually in the industry, we usually look at the net calorific value, but we need basically the fuel composition to some degree. And also, if you want to calculate the air access ratio, we need what's called the minimum air requirement, which is also only dependent on the composition of the fuel. And this means that every gas-fired combustion process is in principle always designed and then later adjusted for a specified fuel gas in order to fulfill its purpose in a safe, efficient, and environmentally friendly way. Now, let me say a few words about adjustment because it's really important here. Whenever you put a process into operation for the first time, no matter if you talk about a residential heating appliance or a gas stove or an industrial furnace or a gas turbine in a power plant, these systems, these processes are always adjusted, which means that the volume flows of the fuel and the oxidizer are set in such a way that the device fulfills its purpose with optimum performance. So optimum efficiency, lowest possible pollutant emissions, getting the temperatures right that where you want them to be, getting the product quality that you want, because if you think about industrial processes, this is usually combustion process heating is a means to an end, so we have to consider product quality. Combustion equipment is always adjusted when the system is first commissioned and after maintenance or after repairs. Next slide, please. And this has a certain consequence when we think about gas quality, because as an end user, I do not really care about the national specifications of gas quality in a large geographic region, like let's say like on all of Germany or even all of Europe. I'm much more interested about what's happening at my location at this moment in time. And I'm also much more interested about the relative change of the local gas quality compared to the gas that my system was originally adjusted for. And this is a very different perspective compared to what the gas industry does, because if you look at the specifications of gas qualities in Germany or in Europe, they tend to talk about large geographic regions, and they tend to talk about absolute values. They want to give you the minimum and maximum permissible Wobbe index, or the minimum and maximum gross calorific value, or a minimum methane number, or something like that. As an end user, this is nice to know, but it's not really relevant for me. But because for me, it's really about a relative change of the local gas quality compared to to what my gas was originally adjusted for. And because my system was designed and adjusted for a specific fuel, it means that if there's a change in the local gas quality, which would mean, for example, a change in the firing rate or a change in the access ratio, unless I respond to this change, this would mean that that there will be an effect. So my performance will maybe not be as good as I want it to be in the design point. Obviously, the stronger the fluctuation, the stronger the consequences of the gas quality change can be. And it's also relevant or important to know when we talk about consequences, it's not only about safety, it's about loss of efficiency or maybe higher pollutant emissions. When we talk about industrial gas utilization, we're usually less concerned about carbon monoxide. We're usually more concerned about things like NOx, for example. It can be product quality, which may be affected in one way or the other, or it could also, of course, be safety issues. Next slide, please. Now, obviously, there's a big difference if you look at residential equipment compared to industrial equipment or to equipment in power plants. And these differences are also reflected in the way that these systems are adjusted. For example, if you look at the residential sector, gas-fired heating appliances or also stoves are usually operated and adjusted for very high access ratios. So we have access ratios of something like 1.2 to 1.4. So 20 to 40% more air than theoretically needed, which is a lot, but it makes sense if you look at how residential appliances are being used and if you look at who is using residential appliances. And second main difference, at least in theory, these appliances are adjusted by the manufacturer on the factory floor to a specified gas quality, which is usually a reference gas, G20, specified in EN 437, which means basically pure methane. I say here it's supposedly adjusted by the manufacturer because we know that in practice, many installers still adjust residential appliances on site based on an unknown gas composition, which you can do. You don't need to know the gas quality in order to adjust an appliance. You can use the output data from the process to do that. But at least in theory, residential appliances should be adjusted by the manufacturer and then sealed and then shipped to the final destination. Industrial combustion processes, however, have to operate with much lower air access ratios. So we usually have air access ratios of something like 1.05 to maybe 1.15. In some cases, we actually intentionally operate these systems with lack of air, usually due to process-related reasons. Maybe we don't want to have oxygen in the furnace to come into contact with the material that we are producing. And industrial equipment is always adjusted to the local gas at the time of commissioning, usually without even knowing what that gas is. So we always adjust industrial equipment to the local gas, whose quality is usually unknown. And the reason for that is that we have much more challenging operational requirements. We have much more challenging requirements in terms of efficiency, in terms of pollutant emissions that we have to comply with. Product quality is, of course, a big concern. And we need to do this with the actual gas. So not with some kind of theoretical reference gas, but we need to do this with the actual gas. And this adjustment to a reference gas like G20 only makes sense and only really works if you have a high access ratio, which we cannot afford. Of course, our systems still have to be safe, but safety is usually assured in a different way by much more in a way of measurement and monitoring and control. And of course, you also have qualified personnel on site that can intervene if something really goes wrong. But the low air access that we have to work with means that our processes are more sensitive to gas quality changes because, in a way, air access ratios are something like safety buffers. And we have to work with a lower safety buffer compared to what the residential sector does. As I said, we need these low access ratios for efficiency reasons, for low NOx reasons. Sometimes it's also a question of the O2 concentration in the flue gas, which can have an impact on product quality as well. So these low access ratios are non-negotiable for us in the industrial sector, but they make our systems systematically more sensitive to gas quality changes than what you see, for example, in the residential sector. Next slide, please. So I've been talking about gas quality, and if you look at the discussions about gas quality, usually the VOB index has a very prominent role in these discussions. The VOB index was originally introduced as a very easy way to assess the impact of a fuel change on the heat release on a simple, uncontrolled combustion process. By definition, it means that if two gases with the same have the same VOB index are burned at the same nozzle with the same nozzle pressure, they will release the same amount of heat. So these gases are interchangeable in terms of heat release. I can use a simple gas combustion appliance with both gases without having to physically change the hardware, which is a perfect definition for the residential sector, because that's exactly what's needed there. So the VOB index is extremely important from the residential or commercial end users perspective. It is also to some degree relevant for larger industrial applications, but not to the degree that we have in the residential sector. So if you talk to industrial users about gas quality, they will usually focus more on calorific values, for example, or maybe methane numbers if you're thinking about gas engines. But the VOB index, at best, from their perspective, is one fuel quality criterion amongst many. And the reason is that the VOB index only really considers heat release. So many other important aspects of a combustion process are not described, cannot be described by the VOB index. So the VOB index doesn't tell you anything about safety, about emissions, about efficiency, about temperatures, about combustion stability. And especially in the current discussion about hydrogen, we have to keep in mind that the VOB index is only really meaningful for chemically similar fuels. So it makes sense to look at different LNGs in the context of the VOB index. It makes sense to look at the differences between L gas and H gas looking at the VOB index. But once you start talking about chemically very different fuels, like for example methane and hydrogen, then the VOB index is far less meaningful. And I want to show this on the next slide with a brief example. What you see here, these are 4 different fuel gases. So we have methane as a representative for natural gas. We have hydrogen. And then we have 2 blends here of methane with either CO2 or nitrogen. And these blends have been prepared in such a way that they basically have the same VOB index as hydrogen. But look at all the different fuel properties. Look at the calorific values. Look at the adiabatic combustion temperatures, for example, or also SL, which is the laminar combustion velocity, which is important for flashback, which is a big issue with hydrogen. So you can see that although the VOB indices of the 2 blends and hydrogen are basically identical, these 2 blends behave still like a natural gas and not like hydrogen at all. So please keep that in mind when we talk about chemically very different fuels, and hydrogen is a prime example here, then the VOB index is not as meaningful as you might think looking at gas quality regulations. Next slide, please. Okay, this is just to highlight some of the key differences. If you look at it from the end-use perspective, go to the next slide, please. So what does all this mean if we think about gas quality, if we think about LNG, especially maybe in regions which are not used to getting LNG? And this is an example, it's an older example from France. France has some experience with strong locally fluctuating gas quality. So this is an example from 2016, where the grid operator noticed that they had seen 5 major changes of the local gas quality at one measurement point within 2 days. And a major gas quality change here means something like 2 megajoules per cubic meter, which is about 4% of the VOB index. This, if you look at what's permissible in European grids right now by looking, for example, at the Easy Gas Common Business Practice or what's going to be in the upcoming EN 16726, this is still a relatively moderate change, but from an entry range perspective. But still, for an end user, this is already a very significant change. And let's see what happens if we wanted to operate an industrial piece of combustion equipment with these gas quality changes. Next slide, please. So let's assume I run some kind of industrial furnace, a glass melting furnace like down here on the right-hand side, or maybe some kind of heat treatment like the picture on top. So something, a larger industrial furnace, and I adjust it to the locally available gas, which at the moment may be pipeline gas. So with a Wobbe index of 50.4 megajoules per cubic meter, and I adjust it to a reasonable access ratio, something like 1.05. So what happens to this system if now it's being exposed to LNG with a much higher Wobbe index of 52.7? We're for the moment here assuming that we don't have any combustion control, which you really should have with such a furnace, but I want to show why we are so sensitive here to gas quality variations. So if my system, which was adjusted to pipeline gas, is now being confronted with LNG with a higher Wobbe index, what that means is that, first of all, my firing rate will go up. So I put more energy into the system, which can be a problem, but must not necessarily. What really is going to be a problem is the access ratio here, because my access ratio drops from 1.05 to 1, which means I'm running my system basically at stoichiometric conditions, which is an unsafe state because I'm going to produce a lot of carbon monoxide here. So this is definitely a safety-related issue here. There are other consequences. The flame length is going to increase quite significantly if I reduce the access ratio. And keep in mind, this is industry, so product quality is key here. So I may have an impact on product quality because I have less oxygen in the flue gas than I want to have. Of course, this could also go the other way around. So next slide, please. So for example, it could happen that I've adjusted my system to an access ratio of 1.05 when I was being supplied with LNG. So the question now is, what happens if I now switch back to a gas with a lower calorific value, again assuming no combustion control? Now just the opposite thing happens. My access ratio goes up, which is a good thing because at least my system is not inherently unsafe. But I have reduced the energy input into the system, so I will probably produce less than I want to. I will likely have an increase in NOx formation because I'm injecting more air into a hot environment. My flame length will be reduced, my efficiency will be reduced because the lambda value and thermal efficiency are directly connected for high temperature processes. And again, I might also have an impact on product quality because this time because of an increased O2 content in the flue gas. So this is just to highlight why we in the industrial sector tend to be much more sensitive to gas quality changes than, for example, residential appliances, which just operate with more excess air, which makes them more robust in this way. Next slide, please. And this is also being reflected by industrial standards. So for example, this is a snippet taken from the European standard for forced draft burners for gaseous fuels. I don't want to go into all the details here, but what you see quite clearly is they only talk about local gas qualities and local gas quality variations. They say if the local gas variation exceeds a certain limit, they will no longer be, or they can no longer guarantee CO emissions, flame stability, equipment lifetime, efficiency, NOx emissions, and note also this what they consider to be a significant local gas quality change. They talk about something like plus minus 2% in the Wobbe index. So much narrower than what we saw in Jose's slide about LNG qualities, and definitely much narrower than what we have, for example, in the entry range of the upcoming EN 6726, or what we have in easy gas, or what we have in German gas quality specifications. So we have a significant mismatch here between the requirements on the end use side and the gas quality specifications that are in place today. And what they say, if you have a stronger fluctuations than plus minus 2% of the Wobbe index, then you need to think about combustion optimization, which basically means combustion, which often means combustion control. Next slide, please. And this is basically just a slide that Jose already showed. Keep in mind that we have conflicting injections now, because if we include more LNG in the future, then LNG traditionally has a relatively high Wobbe index, a relatively high calorific value. At the same time, we're also talking about injecting more and more renewable gases, so like biomethane, synthetic natural gas, or blends of natural gas and hydrogen. They tend to go towards the lower end of the Wobbe index or calorific value ranges, which means that as an end user in the future, it's going to be more likely that I'm going to see stronger changes than today, simply because I will have probably more gas injected at the upper end of the Wobbe index range, and I will also have more gases being injected at the lower end of the Wobbe index range. So as an end user, I have to prepare for stronger local fluctuations depending on where I am in the grid, and depending on the grid topography, and of course depending on flow patterns in the grid. Next slide, please. Of course, now the question is, what do you do about it? Because we have to address this in some way, and this is actually a real-life, or it's inspired by a real-life example from Germany, where we had this case that the operator of an industrial furnace noticed that sometimes the flame in his furnace would increase in length quite significantly for no apparent reason, and he couldn't understand why, because he hadn't changed anything. So he started investigating, and at some point he figured out, okay, it's actually the gas that I'm being supplied with that causes these changes in the flame length. This was located in eastern Germany, so traditional Russian gas region, and his furnace was adjusted to Russian gas, and it was adjusted in such a way that it would always keep the volume flows of fuel and oxidizer constant, independent of the actual gas being supplied, independent of the pressure. And he noticed that whenever he was being supplied with North Sea gas instead of Russian gas, the flame length would increase. What's interesting here is that the Wobbe indices of both gases are basically the same, but for this furnace, the Wobbe index as a gas quality criterion was relatively uninteresting. What's actually more interesting here is the calorific value, and North Sea gas has a calorific value which is about 4% higher than Russian gas, and we wanted to figure out, okay, what's happening here and what can we do to deal with this issue. So what we did was we recreated this case in a small CFD simulation. So this is data from a computer simulation, just because it's easier to visualize this. And we started with the reference case. So basically we created a small industrial burner, adjusted it for Russian gas with an AX ratio of 1.1, a firing rate of 200 kilowatts. And then we switched to North Sea gas, but we kept the volume flows constant. So what happens if you have a higher calorific value? Of course, the firing rate goes up by 4%. The air access ratio goes down by 4%. So I wouldn't have needed a computer simulation for this, but look at the flame. The flame increased by about 20%. And this is exactly what the operator of this furnace observed in real life. So this is the explanation why this gas quality change caused this different combustion behavior. And then, of course, the question is, what do you do about it? Well, the one obvious answer is combustion control. So we assumed we had some kind of gas quality measurement device in the system. So nothing fancy. You don't need a gas chromatograph for this or something like that. You just need some information about the calorific value in this context. And then we said we have some kind of control setup which allows us to change the volume flows of the fuel and the oxidizer independently from one another to keep the firing rate constant, to keep the access ratio constant. And look what happens. Next slide, please. So basically, that's what we recreated in our simulation. And as you can see, of course, now the firing rate is where we want it to be. The access ratio is what it was supposed to be. But also the flame length is just as it was supposed to be. So this highlights how we can use combustion control to deal with these issues. But we need to have some kind of information about the local gas quality. And we need to have the means to respond to the gas quality change. So this is about, first of all, detecting a gas quality change and then responding appropriately to the gas quality change. And I want to show you the next slide, in the next few slides, how this can also go horribly wrong if you don't have a proper control setup, because not all control systems or not all combustion control systems are created equal. Many industrial control systems were never really designed to take into account gas quality variations. And this is one example. This is actually a glass melting furnace from Spain. It's an oxygen furnace, so they run with pure oxygen instead of air, but it doesn't really matter for our discussion here. So they started great because they had a local gas quality measurement device which detected that their being that the calorific value of the gas that they were being supplied with changed by about 5%. So they had a 5% increase in the calorific value, and they responded perfectly by reducing the volume flow of the gas by 5% in order to keep the firing rate right. So perfect response, just as you should. Next slide, please. But then things go wrong, because now they had what's called a fixed ratio control. So basically, they had a setup which keeps the firing rate and the which keeps the volume flow of the fuel and the volume flow of the oxygen at a fixed ratio, at a fixed ratio, which is something that you don't want to do if the gas quality actually changes. This is a control approach that you use if you want to change from full load to partial load, or maybe to overload. So if you change load patterns, then this is a reasonable approach. But if your change is caused by some kind of gas quality change, then this is the completely inappropriate response. So what happened? The firing rate goes down, the volume flow of the fuel goes down by 5%. The air excess, the volume flow of the oxygen goes also down by 5%, which means that the excess oxygen is reduced to 0. We see the blue line here. So the system becomes substoichiometric. And then if you look at the next slide, you will see what's the consequence is going to be. The system slips into substoichiometry. We produce extreme amounts of CO. I don't know if you can see that here, but they started producing about 37,000 ppm of CO, so way beyond any safety limit. The system couldn't get into a stable state again because we had conflicting control activities. And in the end, what happened was that the furnace operator had to shut down the control system at all. They had to go manually intervene, and in order to bring the system back into a safe state. And as you can see, if you look at the x-axis, they had a lot of fluctuation there, so it took them an extremely long time to get the system stable again. And in fact, even after about 7 hours or so, the system still saw significant fluctuations. So this just highlights that if you think about combustion control in terms of fluctuating gas qualities, you need to be sure that it's an appropriate gas quality control, combustion control, which can really take into account gas quality variations. Next slide, please. And this is something that many industrial systems still don't have, because for the many industrial systems still work with fixed ratio control, because their control systems are primarily used to change loads, but they inherently assume a constant gas quality. And especially if you think about different LNGs or changes between LNG and biomethane or something like that, then a fixed ratio control system will not be able to deal with that. So this is something to keep in mind when we talk about gas quality changes from an end user's perspective. This is really something that we need to address, and where also the support of the gas industry is needed, because these are discussions that are often quite new for many industrial end users. Next slide, please. And I think the next slide should be the last one. To conclude, natural gas and energy utilization is extremely heterogeneous, extremely diverse. Especially when we talk about industry and power generation, gas-fired large-scale equipment is operated under very different conditions and constraints than residential appliances. And for end users, it's usually about the relative change of the local gas quality, which is important. So end users don't really care that much about the minimum Wobbe index, permissible Wobbe index in Germany, or the maximum permissible Wobbe index in Germany, or the minimum calorific value or the maximum calorific value. They really are much more interested in what's happening locally. How different is the gas that I'm being supplied with right now compared to the gas that my system was originally adjusted for? Generally speaking, and this is also to some degree the case for residential equipment, but it's much more severe for industrial equipment, the acceptable gas quality variations tend to be of the equipment tends to be much smaller than what the regulations allow into the grids. Of course, the question is also, what is an acceptable gas quality variation as well? We need to keep in mind that from an end user's perspective, especially when you think about industrial or power generation end users, The WOB index is not as important a criterion as in the residential sector. So calorific values can be extremely important. Methane numbers can be important for some applications, especially if you think about gas engines. Gas quality variations can be controlled, can be dealt with. I've shown you one example, which is combustion control, appropriate combustion control. It can be a very powerful tool to deal with gas quality changes. There are other tools available. You could think about local or even grid level fuel conditioning, for example, how they do it in Japan or in Korea. Of course, this is a significant cost factor if you wanted to adjust fuel quality in an entire country. Some countries do that, but for some countries, this is easier to implement than others. You can also think about local gas quality conditioning, which is something that's being done by some industries which are extremely sensitive. So they condition the incoming gas quality to the gas quality that they want by mixing it with LPG or with air to get just the calorific value that they want or just the WOB index that they want, and then they can compensate gas quality fluctuations that way. We can think about grid level measures like improved availability of real-time gas quality information on a reasonable spatial resolution by maybe maintaining sort of constant flow patterns in grids as much as possible. So there are quite a few ways how to deal with gas quality variations. As end users, we tend to be more sensitive to the local variation. And this is also why the upcoming EN 16726, for example, does not only talk about entry ranges like previous gas quality specifications, but also specifically talks about exit points, because from an end user's perspective, this is usually the more important aspect to deal with their gas utilization. And I think with that, I probably have talked too much already, but thank you for your time. And I'll be happy to discuss this in much more detail if required and if you're interested. Thank you very much.
Thank you. Thanks a lot, Jörg, for your presentation. I think we are grateful for the time and your effort you took to share your thoughts and experience with us. You've got actually the congratulations coming from Christoph in the chat already. So
thank you very much.
Just wanted to mention it.
I don't see the chat. I don't know. If I get an error message if I want to open the chat. So if there's any questions in the chat, somebody has to read them to me.
Okay, so it's why I read it for you.
Okay, thank you.
So, dear colleagues, it's time for your questions. I will come back to the chat because we received 3 questions on the first part from questions to Jose. I've seen that you already started to answer them, Jose, but maybe we can just share them with all the group. The first question is about actually the needs to measure oxygen on LNG terminals, because as you said, we had some experience with oxygen in some cargoes. So is it necessary to mention it, to measure it, or to do something about it?
Well, as I said in the presentation, in recent years, in some cargo manifestos has appeared oxygen in the LNG composition. Oxygen has never been present in LNG, so most of the LNG terminals has not equipment to detect oxygen. As far as I know, this has been on the table for some time, but seems not to be a problem, at least from the point of view from the side of the LNG terminals. Anyway, if oxygens appear in higher amount in the future, I'm sure that the LNG terminals will take measure as a minimum to analyze and to give the information, as Emmanuel said. Now is requested by the EU regulation to inform about the content of oxygen in the natural gas. So if this is really a relevant component, for sure the LNG terminal will give the information.
Okay, thank you. There is another question from Ribor about how many LNG samples are actually taken into account for the analysis from one cargo.
Well, as I said, or I tried to say in the chat, I'm not completely sure. This will depend on the procedure established in the different LNG terminals. But normally, the analysis is performed using a gas chromatograph. So a minimum of a sample each 15 minutes could be a reasonable figure. Perhaps more, because there are modern gas chromatographs are faster than old ones, and cargo turn load will last between 8 and 12 hours normally, or more in the big LNG carriers. So I think it's a continuous measurement with the limitation of the gas chromatograph.
Okay, thank you. And what about our LNG terminals? Are they ready for oxygen? Sorry, not oxygen. It was the first question. For hydrogen or ammonia?
Well, as I also tried to explain, LNG terminal is designed for managing LNG. But anyway, all the LNG terminal operators are aware that we are in an energy transition in which hydrogen, ammonia, or any other hydrogen carrier will be important in the future. So as far as I know, if not all, most of the LNG terminal owners are studying how to adapt the LNG terminal to these new molecules. Of course, this is not necessarily a cheap process, but could be done. On the other hand, you have new LNG terminals, like the one under construction in Germany, in Stade. I think in the permission granted to the owners of this terminal was requested that the terminal should be ammonia ready. So from the beginning, from the design and engineering phases of the terminal, you are considering ammonia. And this will have implication in the type of equipment that you choose, the materials, and a lot of implication. So in due time, this terminal will change from LNG to ammonia. I'm sure that not for free. Additional investment will be needed because LNG and ammonia are quite different molecules. I don't know what will be needed to change, but for sure will be something more complicated than to close one valve and open the next one. But will be cheaper than with one of the current LNG terminals. But yes, I know that all the LNG terminals are studying how to adapt the terminal for the new molecules.
Okay, thank you. I've got a question from Diego to Jörg. Actually, how strong is the impact of the local biogas or biomethane injection in comparison with the LNG gas quality variation?
Well, it can be quite significant because of course, it depends on the LNG. Obviously, it also depends to some degree on the biogas. For example, in Germany, we tend to condition biogas to a certain calorific value, which is something that other countries don't do. But in the end, it's always about the difference. So and this was the example that I wanted to show from France, which is basically about sort of Russian gas or biomethane versus an LNG. As you can see, the stronger the difference in the VOB index or the calorific value, the stronger the impact is going to be, unless you do something about it. So, for example, that's why I said that in this example we don't have any combustion control. But so you don't have to, or you can respond to this, but you need to know how. And then it's really dependent on what kind of equipment you run. For example, if you have, let's say, a gas turbine, which tends to be extremely sensitive, or a glass melting furnace, which is also generally considered to be one of the more sensitive end-use cases, then the effects will be more significant than if you just run a big boiler to produce process steam, which is usually much more robust in that way. So when we talk about gas quality, it's one thing to talk about how different are these gases that we're talking about, and then the second question is, do I have some kind of way to deal with this by control, by conditioning, whatever? And then the third question is, how sensitive is my process to begin with? And there have been studies in Germany, also in France and in the US, for example, that try to classify different end users in terms of sensitivity. And you can see that some, first of all, generally speaking, the stronger the change, the more significant the impact is going to be in all likelihood, which I think is logical. And but also you can see that some applications are considered much more sensitive than others.
Okay, thank you. I've got a question from Manu to Jose. It's about the uncertainty. Are the uncertainties in measurement of LNG composition reported in the LNG quality database?
No, the uncertainty in the measurement is not in the database because we don't require this data. I think it could be a bit difficult to compile. What we have presented is the standard deviation. Of course, this is not all the measurement. This is not the uncertainty, but can you give you an idea about the variation? But anyway, any LNG terminal is measuring LNG quality because they need to determine energy downloaded in the LNG terminal. So the uncertainty associated to this measure should be inside the contract agreement between the owner of the LNG and the terminal. And as far as I know, this is an amount that is quite low because it's a very sensitive commercial issue.
Yeah. Okay.
So, and as far as I know, I don't have in my mind the data, but all operators try to have the uncertainty of the errors in the measurement as low as possible.
Okay. Thank you. And I've got another question for you, Jose, from Christophe, who asked, well, actually, you analyzed many US cargoes. So is it possible to give a composition of the different liquefaction plants in US?
We include this field in the questionnaire as a voluntary field, not compulsory, because we want to know composition for country, not by liquefaction terminal. And yes, I have said that I have that information, but we have not published it because we consider that this could be sensitive, commercial sensitive. What avoid in the past that GANL database was updated was due to commercial issues. Normally, be aware that the owner of the LNG is a shipper company and perhaps don't want to give information about what contract they have with which country or which terminal. So in order to have this information, we try to give the information in the most anonymous way possible. Of course, the information is there.
Yeah,
And in the case of I can say that in the case of the French information, that is one of the countries which more information provide to the database, this information was there. So Christophe could try to ask your colleagues in France, and if I'm sure that if they can, that I'm not sure if they can give you the information.
Okay. Thank you. I've got a question to Jörg. Actually, can the experiences of the gas utilization in the industrial sector regarding gas quality could be transferred to the gas-based power generation, which means gas turbines or gas engines?
To some degree, yes. There are, I mean, technologically wise, a gas turbine is a very different thing compared to a glass melting furnace or to a steam generator. And there are some aspects in power generation which are sort of unique because usually there can also be effects which are associated by pressurized combustion, like in a turbine or in an engine. So you can have kinetic effects which tend to play a much bigger role in pressurized combustion compared to combustion with at ambient pressure. But So what usually happens is that the timescales in which a power plant has to respond to a gas quality change are usually much smaller than in an industrial furnace, because an industrial furnace is thermally relatively inert. So it takes some time to see a change. But to some degree, yes. And I know that we've already had discussions with power plant operators who look into this, and they say, first of all, they need some kind of gas quality measurement, because you need to know the incoming gas quality in order to be able to to respond. And then some of them start to think about conditioning. Some of them start about some kind of a control approach. What you do in the industrial gas turbines, for example, is also sometimes that you preheat the fuel, which is usually something that you don't do in an industrial furnace. But by preheating the fuel, you can sort of compensate for some gas quality changes, which is an option that they have that we usually wouldn't have in an industrial furnace. So there's some overlap. There are also some, of course, quite a few differences. But that's usually always the case when we talk about gas quality in large-scale combustion processes. It's usually highly specific. So there are some, so there are some quite a few similarities. It's also a similar discussion if you think about hydrogen admixture. As long as the hydrogen admixture is not too high, we can treat that as a gas quality issue. Of course, if you switch to pure hydrogen, it's a different thing. But if you think about, I don't know, the difference between no hydrogen and 10% hydrogen or 20% hydrogen or something like that, this is something that, from an end user's perspective, in many cases is basically a gas quality issue. Of course, if you go to 100%, then it's a different thing. But so that's also something where we think that we can learn from the experience of the industrial sector in terms of gas quality, also in terms of how hydrogen admixture might affect end users.
Okay, thank you a lot. I don't see other questions. I just see a note coming from Liquefied from Johan. It was just to actually read it. So Liquefied Research Center in Angler Bunte Institute built a setup for sampling liquid LNG at refueling stations for further analysis in the laboratory to determine gas composition and trace impurities and so on. As far as I know, there is this is the only setup in Europe that can take liquid samples and refueling stations during truck refueling. And this will be interesting for any participant. So if you're interested, feel free to contact him. Okay, thank you. If there is no other questions, I will. I think it's time to close, our tech forum. So thank you very much for the presentators. Once more for your speech, Alexander, Jose, and Jörg, of course. And so our session is over. So thank you for your participants, for your time and attention. As I said before, the papers and the recording will be available on the MARCOGAZ website quite soon. So I hope to see you during the next edition of the Tech Forum or within one of the working groups, the MARCOGAZ working groups. So thank you a lot, and see you very soon. And bye-bye.